Hello everyone, welcome back to the channel. I'm super excited to kick off our brand new series on data structures and algorithms. Whether you're a complete beginner or just looking to solidify your understanding, this course will guide you step by step through everything you need to know, starting from the basics of Big O notation all the way to advanced data structures like segment trees and Fenwick trees. All concepts we will learn through animations so that you will not feel difficulties to understand the concepts. So let's look into the topic one by one what we are going to cover. We will start with Big O notations. First up, we'll explore Big O notation, the cornerstone of analyzing how efficient our code is. Here's what we'll cover. Set up C++ development environment in Visual Studio Code. We'll install and configure VS Code, set up a compiler, and ensure you're ready to run C++ programs on your machine. Big O notation introduction. We'll talk about what Big O notation means, why it's important, and how it helps us compare algorithm performance. Understand DSA Greek. Don't worry, this isn't about learning a new language. We'll decode common terms like n, log n squared, etc., so you can read algorithmic complexity like a pro. Understand linear time complexity. We'll look at examples of O, n, complexity and see how an algorithm's running time scales linearly with input size. Simplifying Big O notation, drop constants. Learn why constants are irrelevant in the grand scheme and how to simplify expressions. Understand quadratic time complexity, O, n squared. We'll dissect nested loops to see why they often lead to O, n squared behavior. Identifying dominant terms. Find out which parts of an algorithm matter most when analyzing time complexity. Constant time complexity. Learn about O(1) operations and how they give instant results. Logarithmic time complexity. Explore how divide and conquer strategies lead to O, log n, runtimes. Exponential time complexity. We'll see why O, 2 to the power of n, grows so fast and how to identify it in brute force solutions. Space complexity analysis. Understand how much memory your algorithms need and why that matters. Analyzing nested loops. Dive deeper into loops within loops and see how to evaluate them step by step. Big O for common algorithms. We'll apply Big O to sorting, searching, and other classic algorithms to see real-world examples. Big O for vector operations. Discover how insertion, deletion, and access operations in vectors affect performance. Summary of Big O concepts. We'll wrap up this chapter with a concise recap of everything we've learned. Next, we're jumping into arrays, one of the most fundamental data structures out there. Introduction to arrays. We'll discuss what arrays are and why they're so important in programming. Fixed size versus dynamic arrays. Compare static arrays to dynamic ones, like C++ SSTD vector, and learn their pros and cons. Time complexity of arrays. Find out why accessing an element in an array is O(1) and why insertion or deletion can be costly. Array operations, insert, delete, update. We'll implement these operations step by step and analyze their performance. Multidimensional arrays. Explore how 2D or 3D arrays are laid out in memory and how to work with them efficiently. Memory layout of arrays. Understand row major versus column major storage and why it matters. Searching in arrays, linear search, binary search. We'll compare O, n, linear search with O, log n, binary search and see when to use each. Merging arrays. Combine multiple arrays into one efficiently. Rotating arrays. Practice rotating elements to the left or right in place. Finding the maximum subarray sum, Cadon's algorithm. We'll code up this popular interview question and understand its O(n) solution. Sliding window technique. Learn how to solve subarray problems in O(n) by maintaining a sliding window. Two pointers technique. Another powerful pattern for solving array problems with minimal extra space. Moving on, we have linked lists, a dynamic data structure that offers flexible memory usage. Understanding pointers. Before we manipulate linked lists, we need to grasp how pointers work in C++. Introduction to linked lists. We'll see what makes linked lists different from arrays and when to use them. Time complexity of linked lists. Analyze why insertion at the head is O, 1, but accessing the middle can be O, N. Types of linked lists: singly, doubly, circular. Explore the variations and use cases for each. How linked lists work. We'll visualize how nodes connect and how traversal happens. Creating linked lists. Step-by-step creation of a singly linked list in C++. Practice problems for linked lists. We'll tackle some classic challenges to strengthen your understanding. Displaying linked lists. Implement a function to print all elements in a linked list. Deallocating linked lists. Clean up memory to avoid leaks. Adding elements to linked lists. Insert nodes at the end, beginning, or any position in the list. Removing the last element from a linked list. Carefully handle pointers when removing nodes. Implementing deletion from the end. We'll refine our code to handle edge cases. Refactoring deletion code. Keep your code clean and maintainable. Adding elements to the beginning of a linked list. An O1 operation if done right. Removing the first element from a linked list. Adjust pointers to the new head. Accessing elements in a linked list. Traverse nodes to find the correct position. Modifying elements in a linked list. Update node values in place. Inserting elements into a linked list. Insert anywhere, given a valid pointer. Removing a specific node from a linked list. Search for the node and adjust pointers accordingly. Reversing a linked list. A classic interview question, solved in O(n). Detecting cycles in a linked list. Floyd's cycle finding algorithm, tortoise and hare. Merging two sorted linked lists. Combine them in ascending order. Flattening a multi-level linked list. Handle lists that have child pointers. Partitioning a linked list based on a value. Rearrange nodes around a pivot value. Removing duplicates from a linked list. Use hashing or two-pointer techniques. Converting a binary number represented as a linked list to decimal. A fun problem to practice traversal. Reversing a portion of a linked list. Reverse only a subsection of the list. Next, let's talk about two essential data structures often used for solving real-world problems: stacks and queues. Introduction to stacks. Understand the last in first out, LIFO, principle. Creating stacks. Implement a stack in C++ from scratch. Adding elements to stacks. Push operation and its complexity. Removing elements from stacks. Pop operation and stack underflow. Introduction to queues. Learn the first in first out, FIFO, principle. Creating queues. Implement queues in C++. Adding elements to queues. In queue operation and time complexity. Removing elements from queues. Dequeue operation and queue underflow. Circular queues. Optimize space by making your queue circular. Implementing stack operations using vectors. A practical way to build stacks with C++ STL. Reversing a string using a stack. A neat example of stack usage. Checking for balanced parentheses using a stack. Solve a common coding challenge. Sorting a stack. Learn to sort elements within a stack. Implementing queues using stacks. Demonstrate the relationship between these structures. Priority queues. Handle elements with priorities using heaps under the hood. Deques, double-ended queues. Add or remove elements from both ends. Stacks and queues time complexity quiz. Test your knowledge with a quick recap. Now it's time to branch out into trees, powerful structures for hierarchical data. Introduction to trees and terminology. Nodes, edges, leaves, and other basic concepts. Understanding binary search trees. Why BSTs are so popular and how they're structured. Types of trees: binary, AVL, red-black, tree. A quick overview of different tree variants. Time complexity of binary search trees. Best and worst cases for insertion, deletion, and search. Creating binary search trees. Implement your own BST from scratch. Inserting elements into binary search trees. Maintain the BST property as you add nodes. Searching for elements in binary search trees. Logarithmic search in a balanced BST. Deleting nodes in binary search trees. Carefully handle removing leaf, one-child, or two-child nodes. Balanced trees and their importance. Why self-balancing trees matter for performance. Finding the minimum and maximum nodes. Traverse left or right subtrees to find extremes. Tree traversals, pre-order, in-order, post-order. Visit nodes in different orders for different use cases. Breadth-first search, level order. Explore the tree level by level. Depth-first search, DFS variations. Pre-order, in-order, and post-order traversals in detail. Constructing trees from traversals. Rebuild a tree given traversal sequences. Binary search tree interview questions. Practice common BST-based challenges. Tree data structure, prefix trees. A specialized tree for efficient string operations. Heaps as tree structures. How heaps use tree properties to enforce priority. Time complexity of tree traversals. Big O for visiting every node in a tree. Next, we'll dive into hash tables, the go-to structure for fast lookups. Introduction to hash tables. Learn the concept of hashing and why it's so effective. Hash maps versus hash sets. Compare storing key-value pairs versus storing unique keys. Handling collisions in hash tables. Methods like chaining and open addressing. Creating hash tables. Implement a basic hash table in C++. Designing hash functions. Craft functions that minimize collisions. Inserting elements into hash tables. Understand average O, 1, insertion and possible worst-case scenarios. Retrieving elements from hash tables. Search keys in constant time, on average. Accessing keys in hash tables. Explore iterators and ways to traverse your table. Hash tables for caching. Leverage fast lookups for cache implementations. Time complexity of hash tables. Understand how load factor affects performance. Hash table interview questions. Solve classic interview problems using hash tables. Practical applications of hash tables. Real-world scenarios like dictionaries, sets, and caches. Finding common elements in two hash tables. Efficient intersection of datasets. Detecting duplicate elements in a hash table. Quickly identify repeated entries. Finding the first non-repeating character in a string. A classic string manipulation question. Grouping anagrams using a hash table. Group words that have the same letters. Finding two numbers that sum to a target. The famous two-sum problem. Finding a subarray with a given sum. Use prefix sums and hashing for O, N, solutions. Let's climb to graphs, a versatile structure for modeling networks. Introduction to graphs. Vertices, edges, and the basics of graph theory. Types of graphs: directed, undirected, weighted. Different ways to represent relationships. Representing graphs using adjacency matrices. A 2D matrix approach. Representing graphs using adjacency lists. A space-efficient alternative. Time complexity of graph operations. Analyze BFS, DFS, and more. Graph traversals, BFS and DFS. Level by level versus depth-first exploration. Topological sorting. Order vertices in a directed acyclic graph. Shortest path algorithms, Dijkstra's, Bellman-Ford. Find the quickest route in weighted graphs. Minimum spanning trees, Prim's, Kruskal's. Connect all vertices with minimal edge cost. Detecting cycles in graphs. Identify loops in directed and undirected graphs. Strongly connected components. Decompose graphs into maximal subgraphs. Bipartite graph checking. Test if a graph's vertices can be divided into two sets. Graph coloring problem. Assign colors to vertices with constraints. Practical applications of graphs. Routing, social networks, recommendation systems. Graph interview questions. Popular challenges like clone a graph and course scheduling. Now, let's heap on the knowledge with heaps, often used for priority queues. Introduction to heaps. Learn the heap property and common operations. Types of heaps: max heap, min heap. The difference between max first versus min first ordering. Inserting elements into heaps. Bubble up new elements to maintain the heap property. Removing elements from heaps. Pop the root and restructure the heap. Moving elements down in heaps. Percolate down to restore order. Heaps as priority queues and time complexity. Why heaps are perfect for implementing priority queues. Implementing heaps using arrays. Store a complete binary tree in an array. Building a heap from an array. The efficient O(n) build heap algorithm. Heap sort algorithm. Sort an array in O(n) log n using a heap. Merging k-sorted arrays using heaps. Combine multiple sorted lists efficiently. Next, we look into recursion, a technique where functions call themselves. Introduction to recursion. Basic concepts and when to consider a recursive solution. Understanding the call stack. How function calls are managed in memory. Base cases and recursive cases. Key ingredients for correct recursive solutions. Calculating factorial recursively. A classic example to illustrate recursion. Fibonacci sequence with recursion. Compare naive recursion versus optimized approaches. Recursive binary search. A divide and conquer method for searching. Backtracking and recursion. Solve complex problems like n-queens or subset generation. Practical problems solved recursively. Real-world examples where recursion shines. Recursion interview questions. Master patterns and avoid pitfalls like Stack Overflow. Next, we will look into one of the most important topics of data structure and algorithm. That is sorting. Sorting is fundamental, so let's master sorting algorithms. We will start with Introduction to bubble sort. Simple but not always efficient. Implementing bubble sort. Code the basic O(n)² approach. Introduction to selection sort. Another straightforward O(n)² method. Implementing selection sort. Swap elements to find the minimum at each pass. Introduction to insertion sort. Efficient for small or partially sorted arrays. Implementing insertion sort. Insert elements into their correct position. Time complexity of insertion sort. Best case O(n), worst case O(n)². Overview of merge sort. A classic divide and conquer algorithm with O(n) log n complexity. Implementing merge sort. Recursively split and merge arrays. Time complexity of merge sort. Consistent O(n) log n performance. Introduction to quick sort. Often the fastest in practice, with an average O(n) log n. Choosing a pivot element. Random, median of 3, or first element, what's best? Implementing quick sort. Partition the array and sort recursively. Time complexity of quick sort. Worst case O(n)², but can be mitigated. Radix sort. Sort numbers digit by digit in O(d)n). Bucket sort. Distribute elements into buckets, then sort each. Counting sort. Ideal for small range integers with O(n) plus k complexity. Next, we will look into dynamic programming. Let's optimize our solutions with dynamic programming. Identifying overlapping subproblems. Spot repeated computations in recursion. Recognizing optimal substructure. Break problems down into subproblems that can be reused. Solving Fibonacci with memoization. Store intermediate results to avoid redundant calls. Implementing bottom-up dynamic programming. Build solutions iteratively from the ground up. Solving the longest common subsequence problem. A classic DP problem in string analysis. Solving the knapsack problem. Optimize your selections under capacity constraints. Solving the coin change problem. Minimize the number of coins or find the total combinations. Solving the longest increasing subsequence problem. Track sequences in O(n)² or optimize to O(n) log n. Matrix chain multiplication. Parenthesize matrix multiplications to minimize operations. dynamic programming for grid problems, paths in a grid, obstacles, and more. Next up, we have tries, perfect for string-related tasks. Introduction to tries. A specialized tree for efficient prefix lookups. Tree node structure. Understand how each node holds character data and child pointers. Inserting words into a tree. Build your dictionary one character at a time. Searching in a tree. Check if a word or prefix exists. Prefix matching. Quickly retrieve all words with a given prefix. Deleting words from a tree. Handle removing words without breaking shared prefixes. Longest common prefix. Find the shared prefix among multiple words. Applications of tries, autocomplete, dictionary problems. Power up your search functionality. Now, let's discuss disjoint set or union find, useful for grouping elements. Introduction to disjoint sets. Keep track of elements split across disjoint groups. Union by rank. An optimization to keep trees shallow. Path compression. Another optimization to speed up future lookups. Find and union operations. Core operations to manage sets. Detecting cycles in graphs using union find. A quick method for cycle detection in undirected graphs. Kruskal's algorithm with union find. Build a minimum spanning tree efficiently. Applications of disjoint sets. Networking, clustering, and more. Next we will learn about Fenwick tree, binary index tree. For efficient prefix sums, let's explore the Fenwick tree. Introduction to Fenwick trees. A compact data structure for cumulative frequency tables. Constructing a Fenwick tree. Build it in O, N log N, or even O, N. Querying prefix sums. Get sums up to an index in O, log N. Updating values in Fenwick tree. Adjust elements without recalculating the entire prefix array. Range queries using Fenwick tree. Extend prefix sums to handle intervals. Applications of Fenwick trees. Use cases like frequency counting and range queries. In the learning journey of data structure and algorithm, we next look into segment tree. For more complex range queries, we'll dive into segment trees. Introduction to segment trees. A tree-based structure for interval queries. Constructing a segment tree. Build the tree in O, N, or O, N log N, depending on implementation. Range queries using segment tree. Query sums, minimums, or maximums in O, log N. Lazy propagation in segment trees. Efficiently update large segments without traversing all nodes. Updating values in segment tree. Update a single index or range in O, log N. Applications of segment trees, RMQ, sum queries. Solve problems like range minimum/maximum queries and more. Next we have to look into sweep line algorithms. Shifting gears to computational geometry, we have sweep line algorithms. Introduction to sweep line technique. Process events along a line to simplify 2D problems. Solving line segment intersection problems. Detect intersections in O, N log N. Closest pair of points problem. Find the nearest pair in a plane using a sweep line approach. Skyline problem. Construct a silhouette of buildings in O, N log N. Applications of sweep line algorithms in geometry. From map overlay to rectangle union problems. Finally, let's wrap up with cache algorithms, crucial for performance in real-world systems. Introduction to caching. Why caching matters and how it speeds up applications. Least recently used, LRU, cache. Evict the least recently accessed items first. Least frequently used, LFU, cache. Evict items that are accessed the least often. Designing cache systems. Consider memory limits, eviction policies, and concurrency. Applications of cache algorithms. Real-world usage in databases, web servers, and more. Wow, that's a lot of ground we're going to cover. By the end of this series, you'll have a comprehensive toolkit of data structures and algorithms under your belt, ready to tackle complex coding interviews and real-world engineering challenges. Before concluding this, I would like to tell you, Soon I am going to launch free step-by-step learning platform where you will find all this chapter's handbook. You can refer it while going for interview. If you found this overview helpful, make sure to hit the like button, subscribe for all the upcoming in-depth tutorials, and ring that notification bell so you don't miss a single video. In the next episode, we'll jump right into Chapter 1, Big O Notations, starting with setting up our C++ environment in Visual Studio Code. As this is completely hands-on course, so we have to set up our environment. Thanks for tuning in, and I'll see you in the next video.